All right, so we are picking up with Unit 4. Unit 4 is all about applications of derivatives. So at this point, we have successfully learned how to take derivatives. Now is the important part of calc, which is to apply those derivatives in context. So the objectives for Unit 4 were to be able to explain the meaning of a derivative in a situation. So the other day we practiced okay, what would the units be? So now you want to be able to explain those units. Can you understand rates of change? So these are the related rates problems. Can you approximate linearly? So equations of tangent line, linear approximation. And then do you know when and where it's appropriate to use L'Hopital's? So for whatever reason, they threw L'Hopital's back into this, even though they have those limits of continuity. And ironically, again, 10 to 12% of the exam. So this little application says to drag the slider to the right to see what happens as t gets larger, and then answer the following questions. So you want to find the rate at which the shadow is increasing in length, and if the boy's height on the skateboard in h feet as he rolls away from the lamppost at a rate of s feet per second. So that's Alright, so here's the boy, he's on his skateboard, he's rolling away from the lamppost, that is 15 feet tall, he's moving at a speed of 3 feet per second, the boy's height on the skateboard is 6 feet, so we have a 15-foot lamppost, he is 6 feet, he's moving at a speed of 3 feet per second. So at time 1, 2, etc., he's moving this way. What's happening to his shadow as he moves away from the lamppost? It's getting bigger or smaller as he moves away? Bigger. So we would expect the rate of change. So it says, so then can you answer those two following questions? Can you find the rate at which his shadow is increasing in the length? So again, you would want to set up your problem. So maybe you say the lamppost, the skateboarder, his shadow, and his speed. So what shape would we be creating? Yeah. So it says find the rate at which your shadow is increasing in length. The boy's height on the skateboard is h feet, and he rolls away from the lamppost at a speed of s feet. At what rate is his shadow So this is like our proportions. I tried to make it that line by line. So my lamppost and my skateboarder are numbers. My bases are x and y. So we want to make the shadow a different length than we want to make the lamppost. And the reason for that is because if the shadow and the lamppost were the same variable, then we would end up losing them in our answer. So the width of the entire triangle is W, and you don't have to call it W, you can call it whatever you want. So x plus y is going to equal W. The reason you want to get x and y together is because that's going to create the related rate for the triangle. So W equals x plus y. So we have 15 that's going to relate to W. And then I would set up some sort of relationship between 6 and 1. So you have your big triangle, your little triangle. That allows me to create my skateboarder and lamppost versus lamppost and their shadows. Finding the derivative of my problem or substituting in my problem x and y for w. You then take your derivative and you get x dt is the speed of the skateboard. So we're going to replace dx dt with 3, which is 5 dy dt, which is 2. So what makes this tricky is the skateboarder's movement is different than the skateboarder's shadow. And so that's why you need like 3 variables. And this was like, I think we had one on the test where like a man was walking away, and it was the lamppost, not a skateboarder, but it has very similar ideas. And the problem is if you don't add the third variable, then you end up getting like zeros and like no variable. So then the second question was, if the boy's height on the skateboard is h feet, so now his height has changed. Like now it's not 6, it's h. And he rolls away from the lamppost at a rate of s feet. What would this look like in terms of general statements then? So now we're not going to have a numerical answer. We're going to have an answer in terms of general. So boy's height is h. So everywhere you go to 6, you would now have an h. So you'd replace your 6 with an h, and then everywhere you add a 3, it's going to be replaced with an s. So we still have our same relationship between w, x, and y, but now the only numerical value in that equation is 15. The derivative of a function of a particular value represents instantaneous rate of change. We know this. We know that the value at an instantaneous rate of change has words or interpretations that go with it then. So when we are talking about the meaning of a derivative in a particular situation, it's important to include the following. Sometimes these are referred to as nut. It's noun, units time. So every once in a while you'll hear it referred to as nut. So noun, units, time. The noun is the what. The time is the when, and then the you or your units. So there's some MD or calc teacher out there who's like, make sure you nut the problem. But now you probably won't forget it, so like, okay, now units time. So it says eager rock fans. So there's some eager rock fans are entering a line to buy tickets to see the renowned band Sir Isaac and the Newtones. I think we have had examples of these same names before. They're modeled by this new equation, E of t equals 512.7 e to the negative 0.173t. Good thing I had batteries. Where E of t is measured in people per minute. So again, if it's measured in people per minute, that means that E of t represents a rate. So if you were given this on a problem on an AP test, then E of t is kind of like a first derivative. Because it represents a rate. Which means if you integrated it, you're going to get a position or a person. If you take the integral again, you're going to get like your acceleration or a rate per minute per minute. So it says find E prime of 22. So calculator problem, right? You're going in, you're going to the calculator, you're finding that value. That's not what AP is testing you on. Because we all know you can go to a calculator, plug it in, and find the value. So E prime of 22 is equal to negative 1.9723. What they're checking you on is what are the correct units and interpret their meaning. So remember, if you take the derivative of a rate, then it is a rate squared. So this is going to be people per minute, or people per minute squared. What does it mean? So here's your noun, your units, and your time. So it means that the rate at which people are entering the line, so it represents the rate, it's a derivative, derivatives are always rate, the rate at which people are entering the line to buy tickets is decreasing because the value of the derivative is negative. So noun is the peak rate at which people are entering. It is decreasing. What is it decreasing by? 1.9723 people per minute squared. When? When is this happening? This is happening at 22 minutes. what, when. Related rates. Related rates are another important application to our derivative knowledge. That's why we did implicit review yesterday. So related rates are a part of implicit and chain rule. When you're doing a related rate, the big thing you are looking for is a given or a find. So oftentimes related rates are going to be with respect to time. So a related rate answer is going to have a dt in it, not a dx. So a lot of derivatives are dy dx. Related rates will be dy dt, dx dt, dz dt. They're going to be with respect to time. Hence the related part. So example 2, if the square root of x plus y equals 6 and dy dt equals 2, find dx dt when x equals 4. So we like to rewrite square roots as 1/2 powers. So before we can do anything, we need to find our derivative. We want to find our derivative with respect to time. So 1/2 x to the negative 1/2 dx dt plus 1 dy dt equals 0. Because we're looking for dx dt and we know all of the other information, like we know x, we know dy dt, we can simply plug in here. The problem is I don't know y, but do I even need to find y? No, because what happened to y became a 1 based on derivative. So oftentimes what students do is they end up wasting time, they plug x in here, they find y, and then they don't even need it. So I have 1/2 the square root of 4 in my denominator times dx dt plus 2. So at this point I'm just going to solve for dx dt. We know square root of 4 is 2. So you have 1/4 dx dt equals negative 2 times 4. Dx dt equals negative. The famous conical sand problems. Sand is being dropped onto a conical pile at a rate of 10 cubic meters per minute. So you need to know, first, it gave you the word conical. Second, it gave you a rate. That rate is in cubic meters. Therefore, that rate represents dV dt. If the height of the pile is always twice the base of the radius, so height and radius have a relationship. So again, going back to our code, pile, radius, height. It says the height of the pile is always twice the base of the radius. So that means if the radius is 3, then the height of the pile is 6. The radius is 5. The height of the pile is 10. So therefore, the height is equal to 2r. At what rate is the height increasing? So we are looking for the HDT. At what rate is the height increasing when the pile is 8 meters high? So we're looking for the HTT at h equals 8. So this is a problem where I do not know DRET. So I gotta get rid of R in my equation. I don't know DRET, I can't find DRET, I gotta get rid of DRET. So we're gonna say, instead of H equals 2R, R equals half of H. And then we're gonna replace R with 1/2 H. So we get volume equals 1/12 pi H cubed. And then we're going to derive. But now I can, at this point, take my derivative and substitute in. So we have dH dt equals 5/8 pi. It didn't ask for it, but if you were associating units to that, then dH dt would be meters for H, minutes for time. So this would be meters per minute. Because dH would be meters, dt would be time. And then approximating values of a function using local linearity and linearization. The equation of a tangent line is and always will be y equals f of a plus f prime of a times x minus a. That y minus f of a could be on either side of the equal sign. F prime of a is always our derivative. So again, f of x is our function, f of a is our point, and then the tangent line represents the slope at that point. If a tangent line slope is positive, then the graph is increasing. If tangent line slope is negative, a graph is decreasing. If a tangent line slope is 0, we are at an extrema. If tangent line slope is 0, we're at an extrema. AP multiple choice. Let g be a function given by g of x equals x f of x. So not only are they hitting you with a tangent line, they're also hitting you with a product rule. If f of -1 is 3, f prime of -1 is -2, use the tangent line to g. All right, so we need the tangent line to g at x equals -1. So that means I need g of -1. Because I need the original point. I need my x1, y1. So g of -1 is -3. And then, in order to write a tangent line for G, I need G prime. So G prime of X is first times derivative of second plus second times derivative of first. Now I want to find G prime at -1. So the slope of G prime at -1 is 5. So my equation of my tangent line is y equals G of -1, which was -3, plus G prime of -1, which is 5, times X minus a -1, which is +1. So that's the equation of the tangent line to G. But is that what I want? No, I want to approximate -0.9. So then what we're going to do is say y of -0.9 equals -3 plus 5, -0.9 plus 1. So 1 minus 0.9 is 0.1. So 5 times 0.1 is really like 5 times a tenth. Well, 5/10 would be a, so -3 plus a half would be, I guess you could have done 5 times 0.1 and got 0.5 too. I don't know why, I always turn everything to fractions. I like fractions. I see a tenth better fraction. We hinted on this yesterday because when we were going over that packet from spring break, we had to talk about over and under approximations. So if the tangent line is negative and the original graph is concave down, then we will have an overestimate. If the function is concave up and our tangent line is positive, then we have an under approximation. So I couldn't tell you if in the last example it was an over or under approximation because we, without further information, couldn't calculate G double prime of -1 to know if the graph was concave up or concave down. Because we would need F double prime. So you can only really give this information if you know both the second derivative, the first derivative, and the original. The last part of Unit 4, because for whatever reason they threw L'Hopital's in here, which we've reviewed it so many times, I think we'll all ace the L'Hopital's problems, is L'Hopital. So one last L'Hopital review. It says F is continuous and twice differentiable. If it's twice differentiable, then it is also twice continuous. Remember, differentiability implies continuity, not the other way around. So if I see on an AP test, especially an FRQ, and it has twice differentiable, I'm writing off to it continuous. Like, I want that in my head. This problem it's not so helpful for, but other problems it will. What is the following limit? So what would the limit of that function be? So this is one of those ones where you have to like plug in different parts. So anytime you're doing this, we're gonna just quickly do sub and plug in 0 for everything. know immediately sine 0, 0, 0 squared is 0, 2x over 0. So the bottom is 0. It's whether the top is 0 or not we have to be concerned about. So f of 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. So I get 0 over 0 in my indeterminate form, which means I can do L'Hopital's. So you get f prime x, because remember we derived top and bottom totally separate, minus 1 over derivative of sine is cosine of 2x times the one everyone forgets, derivative of 2x is 2, sine 2x is a chain rule. Minus 2x minus 2. F prime of 0 is, so this is an evil problem because it's 0. Cosine of 0 is 2 minus 2 is 2 times 0. So now we got to do the L'Hopital's again, which you almost should have known because why on earth would they give me f double prime of 0 if I didn't need to use it? And rest is your homework. It shouldn't take very long.